All right, guys, we're back with the last section of chapter 1, section 8, which deals with interpreting graphs of functions. So previously, we talked about identifying functions and finding function values, and now we're going to interpret what are called intercepts and symmetry of graphs and functions, and also interpret positive, negative, increasing, and decreasing behavior, as well as extrema and end behavior of graphs of functions. Now, that's a whole lot of new vocabulary. Some of it might be familiar, and we just refresh you on what that means, but some of them might be totally foreign to you, and that's fine. We're going to go through all of this stuff, talk about intercepts, x and y intercepts, line symmetry, what it means for a graph to be positive and negative, increasing, decreasing, what are extrema, relative maximums, relative minimums, and something called end behavior. So let's first, in this video, talk about interpreting intercepts and symmetry. To interpret the graph of a function, estimate and interpret key features. So in order to interpret the graph, this is what I'm trying to say, there are some key features that we're going to look at and interpret what they mean. Most of the graphs, lots of times, particularly in this section, are involved in a context. There's like a situation surrounding it that the graph is going to model. So it's important to not only identify these characteristics, but what they mean in the context of the situation that they are modeling. So the intercepts of a graph are points where the graph intersects an axis. Think of the word intercept sounding like intersect. So that's where the graph crosses an x or y axis. The y coordinate of the point at which the graph intersects the y axis is called the y-intercept. And the x coordinate similarly, where a graph crosses the x-axis is called an x-intercept. So here's a graph right here. This graph shows the height y of an object as a function of time. So as time passes, let's say it's in seconds, so it goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, so forth and so on. The height of the object goes up and comes back down. So think of it, if you throw a ball up, it goes maybe straight up and straight down. Now, this doesn't model the path, it just shows you how high the object went. It went, you know, if this is 60, this is 70, probably like 73 meters high. All right, so identify the function as linear or nonlinear, then estimate and interpret the intercepts. So let's show you something about the word linear and nonlinear. If you see the word linear, I know the word ear is in there, but also the word line. So a graph that is linear is a graph of a line. A graph that is nonlinear is a graph that is not a line. So this graph is obviously not a line because it has some curvature to it. So it is non-linear. Now the intercepts, where are the intercepts? Well, there's one right here, it's already identified, and there's one right here. Okay, about, it says approximate or estimate. The y-intercept is, well, if this is 10 and this is 20, it looks like the graph starts here right at 15, and that means the height of the object is about 15 meters above the ground. So I don't know, maybe they were throwing an object off of a building or something like that, throwing it up, or off of the roof of a house or something like that, throwing it up, and that's how it's 15 meters off of the ground. The x-intercept over here is a little bit past 7 seconds. So we're thinking about 7.4. If you put 7.5, you know, you're not gonna like fail algebra or something like that. So the x-intercept is about 7.4. Well, what does the x-axis represent? It represents time in seconds. So 7.4, comma 0 is the coordinate of the x-intercept. Now think about this. 7.4 represents the x and 0 represents the y. What do x and y mean in the context of the problem? Seconds and height. So at 7.4 seconds, the object is 0 meters above the ground. What's that mean? Means the object hit the ground, right? So it took 7.4 seconds for the object to go up and come back down and actually hit the ground. Okay, so this graph shows the temperature, let me clear this off, yeah, there we go, y of a medical sample thawed at a controlled rate. Identify the function as linear or nonlinear, then estimate and interpret the intercepts of the graph. So here is the graph of the function, and the temperature is modeled by y, that's degrees Celsius, and the time is modeled by x, which is in hours. Go ahead and pause the video, answer the questions, and hit play when you're ready. All right, we're back. So is the function linear or nonlinear? It is linear because it's a line. Okay, the x-intercept is right here. That's at 1, 0. And the y-intercept is at 0, -5, which is right here. Now, what's the x-intercept represent? The x-intercept is the time at which the temperature is 0. So after 1 second, the temperature is 0 degrees Celsius. Okay, now the y-intercept, remember it's time, or it's time, temperature, or hours, degrees Celsius. So when 0 time has gone by, that means the initial temperature, or when the object was beginning to be thawed, the temperature of the object was -5 degrees. So I'm not going to write all that out and take up another 3 minutes of the video, but that's what you would actually write out. At when the object was initially taken out, or initially sent out to thaw, the temperature of the object was -5 degrees. Cool. All right, the graphs of some functions exhibit another key feature called symmetry. A graph possesses line symmetry in the y-axis or some other vertical line if each half of the graph on either side of the line matches exactly. Think about if you can draw a vertical line through some portion of the graph and it's a mirror image of itself on either side, then it possesses line symmetry over that line. I just realized my other video is on. Let me turn that off. All right. So an object is launched. The graph shows the height y of an object as a function of time x. Describe and interpret any symmetry. Now, if you look, the graph goes up and back down, and you could actually fold, if you could put that on a piece of paper and fold it over that pink dotted line or purple dotted line, it would land right on itself. That is what we mean by line symmetry. So the right half of the graph is a mirror image of the left half of the graph, and that occurs at approximately, well, that line would be at approximately x equals 3.5. Okay? So that would be the line. Remember, a vertical line is always x equals whatever the number is where the vertical line is. And a horizontal line is always y equals whatever the number it is on the y-axis. Okay? And if you notice, it starts at 0, goes up, comes back down, and stops down here at 7. And it looks like the line is about right and smack dab in the middle of that, which would mean it's at about 3.5. So in the context of the situation, the symmetry of the graph tells you that the time it took the object to go up is about equal to the time it took it to come back down. All right, so here's another example. This is the one from the first practice problem, but we're going to look at this graph and interpret any symmetry. Go ahead and pause the video and hit play when you're ready to see the answer. Okay, we're back. There is actually no vertical line symmetry here. Why? Well, no matter where you place a vertical line on that graph, it is not going to be a mirror image of itself. Alrighty? All right. All right, guys. Well, that's it for this first section. In the next video lesson for section 8, we're going to talk about interpreting extrema and end behavior of a graph. So we'll see you there.